In this example, we're looking at a simply supported beam. It's got a couple loads that are acting there at B and C, and the cross section is rectangular. What we want to know is what is the maximum magnitude normal stress in the beam and where does it occur? What's the maximum magnitude shear stress in the beam and where does that occur? So we're going to take this problem right from beginning to end, from soup to nuts here. In terms of drawing our FBDs, we do our equilibrium, we find our reactions, we determine our internal shear force and bending a moment, and then from that we calculate the axial stress and the shear stress. So let's start out with our external reactions. The external reactions, we need to draw a free body diagram of the entire beam first. So I'm going to draw that over here on the side. And the forces we have are going to be the reaction forces there of A, Y, and dy. We have our 15 and 25 kilonewton forces as such. And from that FBD, what I will do is a moment equation about A. We got the 15 kilonewton has a moment arm of 2 with a negative sign in there in front. We have the 25. It has a moment arm of 5. It's in the negative k direction. Then you have dy with a moment arm of 7. And it's a plus sign for equilibrium. We find then that the reaction at D is 155 over 7 kilonewtons. Follow that up with a summation of forces in Y, and we've got AY plus BY minus 15 minus 25 for equilibrium. That sum is a 0. And then from that we find that the reaction force at A is 125 over 7 kilonewtons. So now what we want to do is make a very detailed investigation of our shear force and our bending moment. Hence, we will use our shear force and bending moment diagram. So I'm going to draw those right underneath here. This is going to be my axis for V, and this is going to be my axis for M. Again, this is V, and this is M as a function of X. So let's start out with shear force. We know in the left face, VO is equal to AY, and AY was 125 over 7. V2 minus is equal to VO. There's no distributed load, so that's a 0, so that's still 125 over 7. We know that V2 plus is equal to what it is immediately to the left of there, and then I have a downward shift there of 15. And so that amount gives me 20 over 7. I'm going to do the same thing over there at 5. We have V5 to the left is V2 plus, and that there is no distributed load, so that's a 0. So that's whatever V2 plus was, 20 over 7. And V5 plus is equal to V5 minus our 25. That's our jump. So that's minus 155 over 7. And then finally, over on the far right hand side, V7 is equal to V5 plus with no change due to a distributed load. So this is also minus 155 over 7. And that agrees with AY. AY we drew up on the positive on the right hand face, so that's a negative So all that agrees with what we have got. So it says here that our our shear force is looking like this. We got 125 over 7. There's a jump down here to 20 over 7. And then there's a jump down here to minus like that. Maybe what I'll do is draw this in red so that we can see it. This is how V looks. Bending moment. The bending moment on the left hand side, it's a pin, or it's a simply supported beam. So bending moment is a 0. I look at the bending moment there at 2. It is what it is. It's at 0 plus the integral from 0 to 2 of v over x. And so v over x, I guess I failed to put numbers on here. This is 125 over 7. This is 20 over 7. And this is minus 155 over 7. So that number is going to be 125 over 7 times 2. The bending moment at 5 is what it is at 2, plus the integral from 2 to 5 of v of x d of x. So that's going to be the 250 over 7 plus the integral of that constant term. That's 20 over 7. That's the base. I'm sorry, that's the height. The base there is 3. So this becomes 310 over 7, like that. And then m at 7 is equal m at 5 plus the integral from 5 to 7 of vx dx. So it's 310 over 7. And there's going to be a minus 155 over 7 times 2, and no surprise, that is a 0, because that makes sense, because that right hand is a pin joint, which can carry no moment there on the end. How does that bending moment diagram look? I'll draw this in red here so we can see it. So we know that the it starts out with whatever slope we've got there, 125 over 7. So it's going to be looking something like that. Then between 2 and 5, it's still going up. It's got a positive slope of 20 over 7, which is less. So it's going to be not quite as steep. And then it comes back to a 0 that looks like this. So the key numbers here are, this is the maximum magnitude of the shear force. This number here is the maximum bending moment in magnitude, and that bending moment is 310 divided by 7. So we are in a great position now to look at stress. We've done all of our background work that we need, our external reactions, our internal resultants, and now we look at stresses. So the stresses say that sigma max then is going to be the maximum bending moment. The y value is going to be on the outer surface, top or bottom, either one works, divided by I. And this is going to occur at x equals to 5 meters, and it's going to occur at y equal to 0.15 meters. And the maximum shear stress for the rectangular cross section, recall that's 3/2 the maximum shear stress divided by A, and that's going to occur at x equal to x, I should say a range. It's not going to be at a value. That's going to be between 5 plus and 7 a minus, and it occurs here at y equal to a 0. Where here what we have is the second area moment for the rectangular cross section is 1/12 bh cubed. It's h is the dimension that gets cubed. A is b times h. The maximum bending moment, I should put that in magnitude so there's no confusion here, we said was equal to 310 over 7, and our maximum magnitude shear force is equal to 155 divided by 7. So that's it. We took this one from beginning to end. We found the external reactions. From that, we find the internal resultant calculations of M and V. We figured out where the maximum bending moment was, and that's where the maximum normal stress is going to be. We found out where the maximum shear force is going to be, because that's where the maximum shear stress is going to be. And we used our two equations for sigma and tau in order to calculate those. Again, this is for a rectangular cross section, and so the equation we use for the maximum shear stress is specific to the rectangular cross section.